Hello, I am SeungWon Seo, a researcher from IIXR. Today's seminar will be about the paper titled Physics In. Physics In is a paper awarded the highlight at CBPR 2024. Its goal is to generate realistic indoor layout with high physical interactivity. The following figure is the main figure from the paper. Automatically synthesizing indoor scene is one of the challenges in the field of computer vision and graphics. In the past, this was attempted based on complex rules, but with the rapid advancement in artificial intelligence, ongoing research is being conducted using various AI technology. Indoor scene synthesis research typically aims to generate furniture arrangement that fit a given floor plan as a condition. In the video below, we can observe realistic furniture arrangement being made while staying within the boundaries of the given rectangular floor plan. To address the problem of indoor scene synthesis, recent studies have actively utilized powerful model backbones in their architectures. The most recent work include ARTIST and Diffuse Scene. ARTIST proposed a transformer-based autoregressive approach that generates the position, rotation, size, and category of furniture sequentially. Diffuse Scene, on the other hand, introduced a diffusion-based method that, unlike many previous indoor scene synthesis studies, does not simply treat furniture as 3D bounding box. Instead, it encodes shape feature for use in the generation process. Using the generated bounding box information or shape feature, suitable furniture is retrieved from a database storing object files to construct the final 3D scene. The key focus of previous indoor scene synthesis studies, including these two, has been on enabling models to run the distribution of real-world scenes layout as accurately as possible. This is highly similar to the training approach used in generative models for other domains, allowing the synthesis of realistic and high-quality scene. However, unlike other domains that utilize generative models, 3D indoor scene synthesis faces limitation when merely synthesizing scene layout that resemble reality. Arranged furniture may overlap with each other or extend beyond the floor plan, violating physical plausibility. Additionally, arranged furniture can create restrictions on movement paths, causing accessibility issues. In fact, such issues have often been observed in the results of previous studies. In the three figures below, we can identify these problems. Overlapping furniture. In the highlighted red boxes, incorrect furniture arrangement such as chair overlapping with each other can be observed. Furniture outside the floor plan. Furniture like wardrobe is generated outside the given floor plan. Blocked pathway. The arranged furniture blocks paths within the floor plan, resulting in inaccessible area. Indoor scene synthesis technology must produce physically plausible results, as it can be applied in areas such as creating 3D simulation environments, generating game content, and automatically designing personalized interiors. In particular, the study introduced today, Physics In, emphasized the necessity of such technology to automatically generate environments where recently studied embodied agents can perform tasks and experiments. Let us return to today's feature paper, Physics In. Physics In uses diffusion to generate indoor scene layout that fit a given floor plan. The layout elements generated include semantic label, size, orientation, location, and 3D shape feature. First, they embedded the geometric feature of each furniture object to transform 3D furniture model into latent shape features. To achieve this, they trained a network called folding net, which take the point cloud of object as input. This method is the same as the one introduced in the previous study, Diffuse Scene. For those interested in architecture for reconstructing the point cloud of 3D object, it is recommended to search for the paper on folding net. They aimed for the final stage to complete an indoor scene composed of interactive articulated objects. To achieve this, the author utilized two datasets. The first is the 3D front dataset for model training, And the second is the GA PartNet dataset, which includes articulated objects. The 3D front dataset is an indoor scene dataset composed of various 3D furniture models and is an essential resource in recent indoor scene synthesis studies. However, the 3D furniture models included in this dataset are all static objects, meaning they cannot support interaction like opening wardrobe, doors, or drawers. Therefore, they also use the GA PartNet dataset, which is composed of diverse articulated objects. Using a pre-trained shape feature encoder, they encoded all furniture models included in both datasets. Subsequently, the training was conducted using the 3D front dataset, and during inference, the generated shape features were matched with similar furniture in the GA PartNet dataset and applied. In other words, the model is trained on the latent feature of static object from 3D front, but it can generate scene including interactive object from GA PartNet. Physics scene trains a conditional diffusion model with time embedding T and flow plan embedding F as condition. To achieve this, it used a unit architecture with self-attention block, where T and F are added as condition to every layer of the unit. Mathematically, this involves learning the likelihood of x0 given F with learnable parameter theta. This process includes a gradual denoising procedure, which can be represented in a formula involving a progressive denoising process. The denoising process can be expressed as a Gaussian distribution defined by the denoising transition, mean, and covariance. The model predicts the noise required to transform xt back to the original x0. For a deeper understanding of this process, it is recommended to refer to DDPM. As mentioned earlier, previous studies primarily follow an approach that simply learns to mimic the distribution of real-world data. This often leads to results that violate physical plausibility. To address this issue, PhysicsIn introduced a physics-based guidance function. This guidance function directs the conditional scene generation process using a physics-based guide to ensure the physical plausibility and interactivity of the generated result. To calculate the probability of constraint satisfaction determined by the constraint function xt is assumed to be near the mean and approximated using a first-order Taylor expansion. Through this process, the probability of satisfying the constraint is simplified. The gradient represents how much xt violates the constraints. This approximation process allows the computation of g, which provides the degree of constraint violation and the directional guidance required for the guide function, without directly calculating the probability of constraint satisfaction. In the denoising process of diffusion, it is essential not only to restore the data, but also to adjust it to satisfy the constraint. To achieve this, the gradient g of the constraint is added to the denoising probability distribution introduced earlier. This addition ensures that the restoration process goes beyond merely removing noise, incorporating directional adjustment to satisfy the physics constraint. The physics-based guidance function introduced by the author is divided into three categories. The first is collision avoidance, which aims to reduce object mesh collision in the generated scene. Instead of directly detecting collision using the mesh, it calculates them using the predicted bounding box. Specifically, 3D bounding boxes are obtained using the predicted location, orientation, and size of object, and collisions are calculated using 3D IOU. To provide guidance in the direction of preventing collision, the negative value of the calculated result is used. IOU is calculated as the ratio of the difference between the area occupied by two objects to their union. The example image at the bottom right visualizes the 2D IOU calculation process. The second is room layout guidance, which is necessary for arranging interactive furniture. It penalizes object locations outside the given floor plan. Walls are extracted from the floor plan and their thickness is set to infinity in the direction outside the room. The extracted walls are treated as bounding boxes similar to object, and the collision between object bounding boxes and wall bounding boxes is calculated using 3D IOU, as in the collision avoidance process. The final guidance is reachability guidance, designed to prevent the generation of multiple disconnected regions in the scene. The presence of such disconnected regions implies area inaccessible to users, which poses a problem in indoor scene synthesis. To address this, a cost map for navigable area is first generated based on the arrangement of the furniture using a Gaussian distribution. Points closer to objects are assigned higher cost, enabling the calculation of paths that naturally mimic human movement between furniture. In the cost map example figure, yellow indicated higher cost while white indicated lower cost. Next, the two largest disconnected regions are identified, and their center points are set as the start point and end point for pathfinding using the A-star algorithm. From the generated paths, L points are selected and bounding boxes are created at each point, considering human physical dimensions. Penalties are then calculated based on the collision between the furniture bounding boxes and the bounding boxes selected along the human navigable paths. Using these guidance functions, PhysicsScene performs physically plausible indoor scene synthesis followed by experiment. The experiments are conducted using the two previous studies described earlier in the presentation as baseline. To evaluate the quality of the generated result, the same metrics as in previous studies are used: French inception distance, corner inception distance, scene classification accuracy, and category KL divergence. Additionally, the author proposed new metrics to evaluate physical plausibility. First is collision ratio. Measure the proportion of object collision in the generated scene. Second is scene-wide collision ratio. Measure the proportion of generated scene where object collision occur. Next is out-of-floor plan ratio. Measure the proportion of object located outside the floor plan. Fourth is object accessibility ratio. Measure the proportion of object reachable from any arbitrary point within the floor plan. Last is maximum connected area ratio. Measure the proportion of the largest connected area in the generated scene. This additional metric comprehensively evaluate the layout, suitability, accessibility, and interactivity of the generated scene. In the unconditioned scene synthesis experiment, PhysicsScene demonstrates state-of-the-art results across most metrics. Notably, significant improvements are observed in physical plausibility metrics such as the collision ratio and scene collision ratio. Metrics related to floor plan are not used in this case because the experiments were conducted on unconditioned scene synthesis. The following are the experimental results for floor conditioned scene synthesis. Previous studies often produce physically implausible results. In the figure, red highlight indicate collision between objects. Purple highlight indicate object placed outside the floor plan. Blue highlight indicate furniture placed in areas inaccessible to the agent. The scene synthesis with articulated object experiment is conducted using furniture from the GA-PartNet dataset rather than the 3D front dataset. Each metric is evaluated based on the 3D bounding boxes of objects, considering their maximum articulation. In interactions with articulated objects, it is crucial that no collisions occur with other objects when the joints are fully manipulated. The experimental results show that the output of PhysicsScene perform exceptionally well in this regard. However, as the model does not directly influence The scene synthesis with articulated object experiment is conducted using furniture from the GA PartNet dataset rather than the 3D front dataset. Each metric is evaluated based on the 3D bounding boxes of object, considering their maximum articulation. In interactions with articulated object, it is crucial that no collisions occur with other objects when the joints are fully manipulated. The experimental results show that the output of physics scene performed exceptionally well in this regard. However, as the model does not directly influence the terrain of each articulated object, it does not show significant improvement in the out-of-bounds object ratio and accessibility ratio. To analyze the roles of each guidance function, an ablation study was conducted on the guidance function. Since the guidance functions have different optimization objectives, they perform distinct roles during the layout optimization process, which can sometimes interfere with one another. In the experimental result, using only collision avoidance reports very low collision scores. However, when other guidance functions are included in training, the improvement in performance becomes less significant. The author mentioned that the balance among the guidance functions contributes to the overall performance improvement. However, given the substantial decrease in the improvement margin, optimizing multiple guidance functions simultaneously appears to be a highly challenging task. PhysicsSyn introduced a guided conditional diffusion model for synthesizing physically interactive scene. To ensure the physical plausibility and interactivity of the generated scene, constraints were designed for object collisions, room layout, and interactivity. While experiments demonstrate significant results, some challenges remain. The design of multiple complex guidance functions lead to suboptimal results. Additionally, although interactivity is enhanced by ensuring a wide range of movement, explicit interactions with furniture are still not fully considered. Moreover, beyond articulated objects, the model does not explicitly account for the need for sufficient space during furniture arrangement, depending on its purpose. For instance, a bed is not an articulated object, but inadequate space must be provided around it for accessibility and use, such as lying down. That's all I have prepared for you today. Thank you.